much of your time, but once again, welcome everybody to this last and final training session for the mic, the level 1 wave modeling in training in mic 21 spectral wave. Today you will be entertained just very briefly by Ruben. We'll do a short recap of the previous session, and then again you will be joined by Andrea, who will continue the presentation in Python utilization in regard to data extraction and data analysis of the mic results. And then you may recall that 2 weeks ago, in the third session, Klaus had a introduction with the common faults experience in spectral wave modeling. He will continuing that presentation today as well. So that is the program for today. Yeah, have a recap for the previous session. Some more in-depth presentation on the Python application, common faults in the spectral wave modeling, and then continuing with development and or introduction and development of the local scale spectral wave models, translating the wave condition at the 30 meter water depth towards the coastline for the entire north coast of Egypt. Last week you were introduced to the delta model, and today you will be likewise introduced to the northwestern and northeastern part of the coastal stretch. So that is the program. Please, Ibrahim.
Thanks, Matt. شكرا دكتور سمير، شكرا للبي ام يو والاخوه اللي لسه المدربين ما جوش، يعني الحمد لله لسه على وصول، ربنا يستر ويجوا بدري. المهم بس احنا الاسبوع الجاي ان شاء الله دكتور سمير هتبدا اللي هو الليت باك ان شاء الله. واحنا كنا عايزين نشوف بس الاخوه اللي حاضرين مدى استفادتهم من الكورس، لان المفروض يعني احنا هنوزع شهادات بتاعه كومبليشن للتريننج اللي هو ليفل 1. المفروض بقى اللي يدخل ليفل 2 بعد كده هنبقى ان ايه، المفروض مش كل هيدخل، فاتمنى ان الكل يكون معانا ان شاء الله في ليفل 2. بس anyway يعني انت ممكن تدينا بس فكره كده دكتور سمير في اخر اليوم عن هل الجميع هيكون معانا في ليفل 2 ولا في حد ايه مش هيكمل معانا. ان شاء الله نتمنى كلهم يكملوا معانا ان شاء الله. فبتمنى لهم بقى ان شاء الله النهارده يوم موفق، ويكون معانا الساعه 5 وربع كده ان شاء الله، فربنا ييسر لهم الامور ويستفيدوا النهارده من حضرتك من الاخوه جميعا. شكرا دكتور سمير. ثانكس مات.
Thank you, Matt. As usual, we are going to start with a recap for our previous session, and we are going to start with Robin. Please, Robin.
Yes, thank you, Dr. Samir. I will quickly share my screen just to go through very quickly through the presentation from last week. Sorry, there's been some problem with with PowerPoint. Let me open it again. And this is here and here and here. Yes. So let me move this. Last week I was talking to you about the different sources of data that you can find out there in the business for you to be able to set up and initialize your different numerical models, either hydrodynamic or spectral wave. Prior to pointing to the different sources, I gave you a brief introduction on the different type of models that you can find out there. And this was necessary because sometimes you Google or you do some research in order to look for models, but then you all of a sudden discovered that that model is not providing you with the type of information that you need. So I was showing you that there are different models in the out there in the business. If we talk about the coverage of those numerical models that will provide you with boundary conditions for your model, you had three different scales. You have the global model, you have a regional model, and you have a local model. A global model is a model that covers the entire world and has a coarse resolution in order to have a reasonable computational time while at the same time having a global coverage. Usually those models are used to feed regional models. Then the regional model is a model that it covers a big area of the world, but not in its entirety. And at the same time, is not fine enough to resolve all the little details or features that happen, let's say, along the coastline. That is basically your area of interest. But the regional model, what it will do, it will convert or it will transform those conditions from the global model, which is a coarse model. The regional model will take those global conditions and will, with a bit more of detail, will transform those conditions to the nearshore area, where you have your local model ready to receive those conditions transformed at its lateral boundaries, and then you will run that local model with the global conditions transformed to nearshore by means of the regional model. I was also talking to you about the different types of models within, usually in the global model, you can find atmospheric models, ocean models, and coupled models. An atmospheric model is what the meteorologists use and is basically focused on what is happening from the sea surface and above. So basically it's giving you information about the atmosphere. Which this is, it will give you information about wind, it will give you information about sea level pressure, it will give you information about sea ice coverage. An ocean model, on the other side, it tells you what is happening all over the world below the sea surface. And from those models, you can get information about depth average currents, about 3D currents, about water levels, anything related to the water environment. And then you have the last type, which is the coupled model, which is you take an atmospheric model, you take an ocean model, you put them together, and then in each time step, the information between the two models is exchanged. So at any time step of that model, the influence of the atmosphere on the ocean, and likewise, the effect of the ocean on the atmosphere is represented, which gives you a way more accurate description of the environment at the cost of taking longer time to run. Having said this, after the introduction of the models and the scales, I also show you what's the difference between a hindcast and a forecast model. So basically, the numerical model is always the same. You have set up a certain model, but depending on the boundary conditions that you apply to that model, you will get a certain answer. For example, you pass as forcing hindcast data, which is, let's say, conditions that happened before the day we are running the model, and then you will get hindcast output. You pass to that same model forecast data, and the output from your model will be forecast data. The model is always the same. The only thing that changes is the input. The type of input that you pass is what you will get in your output. Okay, and after that, I was also talking to you about for the different or the main models that you're going to use in here, which are the spectral wave model and the hydrodynamic model. I was listing for all of you the minimum or the strictly necessary boundary and atmospheric conditions that you need to force each of the models. For the hydrodynamic model, you will have to impose lateral conditions like tidal levels and water currents, and atmospheric-wise, you will have to input or pass wind speeds and mean sea level pressures. For the spectral wave model, the input is similar, but it's not the same. For the spectral wave model, you will have to pass water levels and depth average currents, if you want, surface winds, but also at the laterals, you will have to pass or you will have to force it with wave conditions. And remember this, if you don't impose any wave conditions at the boundaries of your wave model, you are more than likely to miss any swell energy that is arriving to the boundary of your area. Because if you only force your model with wind, you will only be reproducing the local conditions or the local waves that are generated by that wind that is blowing on top of your mesh. Nothing else will come into the system. So don't forget to apply wave boundary conditions to your wave model. And after that, I was also talking to you about, or I was listing the different or the main, the usual suspects for you to get forcing for your models, which were basically ERA 5 reanalysis. From ERA 5, I told you that you can get both atmospheric conditions and also wave conditions for your model. I also introduced you to the CFSR system. In the CFSR, I was talking to you about two types of data that you can find in there. You can find wave data based on CFSR, but that data only covers from 1979 till 2009. This data, this information is very good for you to, once you have set up your model and run your model, you can always have a look at the results of this model and see if they make sense. So it's a good point for you to double check. And also CFSR, what provides you with is with wind and sea level pressure from 1979 till present. So it is not limited to just 30 years of data. So with such a coverage of wind speeds from 1979 till present, you can create a good hindcast model forced by wind. But you will still need to, if you're setting up a spectral wave model, you will still need to find wave boundary conditions for your model that you cannot get from CFSR. But for example, you could get them from ERA 5. Recommendation. I don't recommend, or tip, I don't recommend you to mix different types of forcing. For example, if you are using wind from ERA 5, please do not mix it with sea level pressure from CFSR or from any other source that you can do. Atmospheric forcing or wave forcing, they always should come, all of the parameters from the same models. Otherwise, inconsistencies and bad performance of your model is expected to happen. And last but not least, well, I also introduced you to, or talked to you about Copernicus, that Dr. Samir spent quite some time introducing you to the Copernicus program, where you can get lots of models covering with different coverages, either global or regional, for you to get boundary conditions to force either your spectral wave or hydrodynamic model. And last but not least, I also gave you a couple of links or pointed you to two different sources of bathymetric data for you to start setting up your models. And these two sources are eTopo, which is controlled and managed by the American administration. And the other one is the GEPCO bathymetry, or the nautical chart of the ocean. But this program is managed by the European Union. And remember this, the GEPCO or the eTopo bathymetry is very good for you to set up your model and describe deep water and intermediate water. But when it comes to the description of the seabed near the coast, in shallow waters, let's say from 20 meters of water depth to zero or to the shoreline, the data is not that accurate. It's quite coarse. So please do not rely solely in GEPCO bathymetry or eTopo bathymetry or any other type of global bathymetry for the description of the nearshore area. For the nearshore area, you should look for navigational charts, for example, a source of data for you to see how the seabed in shallow water it really is, or also rely on local survey data. So you are involved in a project with a certain client that has an interest in a certain area, and the client says, look, I also instructed this company to perform a survey of the area, and here you are the most recent description of the seabed. With that information, you pass it to your model, you mix it with your GEPCO or eTopo or whatever bathymetry, and then you will have a very nice local model describing the seabed along the coastline the way it should be. Having said this, and I think I went 5 minutes above or beyond my my time. This is all I wanted to recap to you. And again, any other questions that you may have after this lesson or whatever, just contact me and I will be more than happy to answer your questions. Thank you.
Excuse me, Robin, there are one question from Ahmed Salama, please. Yes.
Absolutely.
Here I'm going to ask not use different type of the large condition exactly. So about using the way to modify and type from the global survey.
There are one question that about your advice not to use different data sources together.
Yes.
The question is, what about using the tides from Mike 21 and wind data from ERA 5?
What I meant with that is not to mix for a certain type of data, mix different sources. For example, if we are talking about atmospheric forcing, let's say about wind and sea level pressure, you should not take, for example, wind fields from ERA 5, but then the mean sea level pressure, take it from CFSR. Both of them are giving you atmospheric conditions, but those variables have been calculated by different models. So if you mix, so the ERA 5 wind conditions have been calculated by the ERA 5 model, and those winds that you have obtained in ERA 5 are directly related to the mean sea level pressure that has been computed by that program. And those values are related or completely attached to, for example, the type of grid that was used in ERA 5, the time step that was used in ERA 5, blah, blah, blah. CFSR will give you the same kind of information, wind speeds and sea level pressure, blah, blah, blah. But CFSR resolution, for example, is different. And the internal time step in CFSR is different. So the wind fields that you have obtained in CFSR and the mean sea level pressure that you got in CFSR are directly related to that specific grid and to that specific time step, blah, blah, blah. So what happens that if you mix wind from one source, but mean sea level pressure from another source, it may be that they are not in the real world compatible, in the sense that they never happen in each of the models. And the outcome of your model will be not realistic. So I said, but it is good to have, for example, you choose your atmospheric model to force your model. Let's say, for example, ERA 5, you have a hydrodynamic model, and then you need both atmospheric conditions and boundary conditions. For the atmospheric conditions, this is wind and pressure. You can take either ERA 5, that information from ERA 5, or from CFSR, or from another source. And then you will need hydrodynamic forcing. And that hydrodynamic forcing can come from the microglobal tide solution or any other model that you can put your hands on from Copernicus. So what I want to say again, we repeat one more time, is when mixing, I was talking about for the same type of data, do not mix different sources. But when the data is of a different nature, yes, of course, you can mix, for example, waves from CFSR and atmospheric forcing from ERA 5, because there are different types of environmental variables. But within the same type of environmental variables, please do not mix different sources. Did this answer your question?
Yes, great.
Thank you.
Thank you. Thank
My
you.
pleasure.
Now there are another question, please.
Yes.
After applying the global pricing model between the range of data and the heights, it's a big difference between the results from the global pricing model and the real mission. It does affect the results from the model.
Please again, after what?
بعد ما طلعنا من التايب الجلوبال برايفت موديل ده اكيد مختلفه جدا عن المبدا بتاع الريال ميشن ده. هل ده هيأثر على النتائج ولا لا؟ مثلا طريقه الداتا بتاع الجلوبال برايفت موديل الداتا المخصصه بالفعل سواء في العالمين او في مطروح او حتى في مشيط الداتا مختلفه جدا جدا البايلوت داتا
الداتا بتاع الفايده اللي انت جبتها
الجلوبال برايفت
من بتاع مايك
بتاعت زي ما اتعلمنا المره اللي فاتت. الداتا مختلفه جدا عن الداتا الحقيقيه الموجوده، يعني الداتا الحقيقيه الموجوده رينج 1 من 10 ل 70 80 سم، لكن الجلوبال تايلر موديل بيطلع ثابت داتا ثابت اب وداون عن الزيرو من سالب 30 لحد 30 سم. مش قادر يجي ليفل بس حاجه ثانيه 80 110 دوت عشان ما عملتش كوركشن انا في ليفل دي كده مش بتسيب.
هو انت مش عارف يعني هو اصلا البيتش ليفل تقدر تشيفت ولا بعد ما عملت شيفت
لا لا الداتا اللي انا قريت بقى دي بصححها على الميس كده.
The question is related to his experience with using a Mike 21 tidal level compared to measurements at one point in Egypt North Coast. And he discovered that there are a big difference between the tidal measurements and the tidal data obtained from Mike 21. So what is your opinion about the accuracy of tide 21 of Mike 21 tides in the Middle East?
Okay, we need to consider several things in here. The first one is that you mentioned that you have measurements of the tidal level, right? And then you are comparing those measurements that I assume that come from a tidal gauge. That's the usual device near the coast for you to register the tidal elevation. And then you compare those results with what you get from the tidal global solution. And then you say that when you extract the data directly from the Mike global model, which is, if you have worked with it, you will see that when you go to the tool, you don't see a map of the world. You don't specify any type of boundary conditions of blah, blah, blah. You just have an interface where it tells you what's the location you are interested in and what is the time span that you want to extract from 1950 till 2050, whatever. And then you get your information. There is no other way for you to pass bathymetry, to pass the coastline, blah, blah. Why? Because that is already existing in the, or is embedded in the Mike global model. And bear in mind this word, global, which means if you take a look to the files that Mike Global Tide makes use of, you have two different types. You have one file for you to obtain time series of sea surface elevation or tidal level. And then you have another different file for you if you want to compute depth average currents. In the, at least from my knowledge, in the Mike version 2022, the resolution, the spatial resolution of the model that has been set up to obtain the tidal constituents of the tidal current has a resolution of 0.125 of a degree. Whereas the if you want to get the components for the sea surface elevation, the resolution of that model is half of it, so it's 0.25 of a degree. Which means that if you want to obtain tidal conditions at a certain location, if you are in deep water or intermediate water depth, the resolution of the Mike global model is more than enough. I mean, if you get to have measurements of the water level in intermediate water, let's say in 30 meters or 40 meters, you will see that the model is very accurate. But then if you compare that data against measurements very close to the shore, it happens what has happened to you, that you see a mismatch. And why is that? That's what I told you, that the Mike global tide model is meant to give you conditions with a global resolution, let's say with a coarse resolution. If you really want to see what's the sea surface elevation or the water level and the currents near the shore, remember that you are starting with a global model. So you should expect that the resolution or the description of the seabed and the coastline near your point is going to be very poor because the scale of the model is global. So what you would need to do in this case is to set up a local model with the boundaries a bit far from your area of interest, then pass as forcing to that model, to that hydrodynamic model, the conditions from the global tidal solution. So your boundaries of that model are in deep enough water. And then you transform that tidal signal towards near shore, and then that local model that you have set up will take into account all the features of the seabed and the coastline, and then it will give you in return accurate water levels at your point of interest near shore. Why? Because you have set up a high resolution model that takes conditions from a global model that are applied to the laterals or to the lateral boundaries of your model, and then it converts that information taking into account all the little features of the bathymetry. So again, what I wanted to say is that the global tide model from Mike is not meant for you to directly extract data right next to the coast. Why? Because the resolution of the global model from Mike is not enough to describe all the little features. You should take the Mike global tile solution as forcing for your regional model, or if you push it a bit too far, from a local model that has the boundaries a bit, how is it? The extension of the boundaries are a bit, I forgot how to English today, excuse me. Far from the area of interest, and then make sure that that high resolution model transforms those global conditions to near shore. Did this answer the question?
Thank you, Robin, for your presentations.
My pleasure.
And we are going now to Andrea. Are you ready, Andrea, to recap last session?
Yes.
Last week's session. Please go ahead.
Hello. Yeah. I guess we're gonna start in 6 minutes with the second session. So I can just quickly show what we did last time. Let me share the screen. We discovered the possibilities of Mike.io, that's a Python library, to explore data from Mike simulations. And we see here in the table of contents, we covered already a short introduction into Python, where we saw that we have to install different libraries that are not yet there, that we have to import them, what kind of variables we can create and define, and some interesting data types we've seen, like the NumPy array or the pandas data frame. And then after, I would say, half of the time, we jumped into the Mike.io. So we saw the data structure, and then we started to analyze the 1D time series that is stored in the DFS0 file. And we stopped after we were able to plot the data, and that's also the point where we're going to continue today. Yeah, I guess that's it.
Okay, thank you for your revision. I will make recap for my last week session, and then you are going to start your new session today, okay?
Yeah, perfect.
Thank you. I will share my screen now. Assalamu alaikum. الاسبوع اللي فات اتكلمنا عن الادفانس تولز ان اس دبليو موديلنج، ومينلي كنا فوكسنج على الباوندري كونديشن. اتكلمنا عن نوعين من الباوندري كونديشن، اللي هي الانسنت ويف باوندري كونديشن فارينج ان تايم، والنوع الثاني فارينج ان تايم اند along the line. يعني كمان مش دومين الحقيقه along the line، يعني على الخط بتاع لانه خط. واتكلمنا ازاي نقدر نعمل الملف ده. فقلنا ان السيتنج بتاعه بيبقى من الباوندري كونديشن، بنختار فارينج تايم كونستانت along the line، وازاي نكريت الملف ده من مايك زيرو. بنروح للتولز بتاعت مايك زيرو، تحديدا DFS زيرو، وبعد كده بنختار بلانك تايم سيريز، وبنختار بنعمل سيتنج للبارامترز بتاعتنا اللي هي significant wave height والويف بيريود والويف دايركشن والدايركشن سبريدنج فاكتور، الاربعه دول. وبنحدد الستارت تايم والنمبر اوف تايم ستيبس، مهمه جدا، والتايم ستيب بتاعتي ساعه مثلا. وبس كده بنابند او بننزرت الداتا دي، بنعمل اوكي، وبنروح لتكست فايل او الاكسل فايل، وبنكوبي الكولمز اللي احنا عايزينها، الاربعه كولمز الاساسيين اللي احنا عايزينها، اللي هم فيهم الداتا بتاعتي، الويف هايت والبيريود والدايركشن والسبريدنج. بنكوبي دول الناحيه الثانيه. وانس ان عملنا كوبي، بقى الملف بتاعي جاهز خلاص، بعمل له سيف. وبعد كده بدخل في اس دبليو وسيلكت الفايل بتاعي. مجرد ان عملت له سيلكت وعملت له فيو، هيطلع بالشكل اللي انا كنت شايفه قبل كده. ده اللي هو كنا الجزء الاولاني. اوكي هتلاقي اكسبيرينس في الموضوع ده. الجزء الثاني لو كنا بنتكلم على فارينج الونج لاين، يعني كمان مش بس في التايم والونج لاين، فبيبقى بقى مش دي اف اس 0 دي اف اس 1. بنختار من التول بوكس بتاعت مايك 0 دي اف اس 1 و لاند فايل، وهنا برضه بنختار البروجيكشن بتاع اللونجلات واللوكيشن والحاجات دي. الحقيقه ما لهاش اي افكت، يعني براكتيكالي ما بنعملش افكت على الداتا. اوكي، وبنختار نفس الاربعه بارامترز بتوعي اهو. مهم بس النمبر اوف جريد بوينتس. هنا مثلا لو كانوا اثنين يبقى نختار اثنين بس، نقطتين بس، واحده في الاول واحده في الاخر. وجريد سبيسنج ملوش اي افكت الحقيقه برضه، بس النمبر اوف جريد بوينتس برضه مهم جدا، والنمبر اوف تايم ستيبس طبعا مهم، والستارت والتايم ستيب بتاعتي مش سكند. يعني دي حاجات كلها مهمه الحقيقه بنحددها زي ما حددناها هنا هو كده، الاربعه الاساسيين واثنين نمبر جريد بوينتس في الاول وفي الاخر، وكذلك التايم ستيب نمبر اوف تايم ستيبس. وبالفعل بنعمل كوبي، بس المره دي بالكوبي الاول والاخر مع بعض، يعني الاتش الاول والاتش في الاخر نعمل لهم كوبي من اكسل اهو. وكذلك البارامترز التايم بيريود برضه في الاول وفي الاخر، السبريدنج في الاول وفي الاخر، الدايركشن في الاول وفي الاخر، وكارنز كده بنكوبي الملف من اكسل. وبعد كده بنبقى خلاص جهزنا الملف بتاعنا بتاع الاوفشور بامب. هل في اي تساؤلات عن حضراتكم؟ اوكي، نقدر نبتدي دلوقتي ان شاء الله الايه بتاع النهارده. Okay, Andrea, we are ready now to start our new session with you regarding using Python in Mike 21 data analysis. Thank you.
Perfect. So you don't need a break first?
Yeah, okay.
No, I'm just asking.
I think we can do that. Okay, 5 minutes only. 5 minutes.
Okay, okay, that's perfect.
Okay, thank you. You can start now, Andrea, please.
Yes, I'm already sharing my screen. Do you see it?
Yes.
Yes. So we're going to continue at a point where we stopped last time. So please open the Google Colab. You can do so when you open the Google Chromecast or whatever browser you use. And I guess it should work if you just say Google Colab, and then the file we used last time should pop up, and you select that one. Or you just, on another approach would be you just use the link that I provided last time.
الباسورد بتاع ايه؟ مصطفى بعد السؤال.
لا لا في أكيد. بس يعني
May you give me a sign whether it works or not?
Okay. Just 1 minute.
Yeah.
That's okay? Okay, we're ready now, please.
Okay, perfect. So you see the interface, and probably you see that certain cells were already run. So probably you see this plot as well. But to restart the session, we need to add the data the same way as we did last time. You remember, here on the left, there is this folder icon. And then we go to the folder where we have all the data that I have provided. We select the data and we just drop here in the folder. Can be a bit annoying that we have to repeat it every time we open the session again. But that's just the way it is. If you have done that, I ask you to go to Analyze and Modify Data here in the table of contents. That's the point where we stopped last time. And now we run everything that we have run before. To do so, we open here the runtime thing, and then we say run before. And then all the code that we discovered last time is running. So we import all the data, we import all the, we install first the libraries we installed last time. It's just going through so that we have exactly the same point as we stopped last time. While it's running, and I hope there are not too many errors, I can continue with like what we're going to discover. So first, I want to show you that there is a quite cool feature that gives you automatically some basic statistics from your time series. You remember last time we read the DFS0 file, and then we have also plotted it, so like the water level. And then sometimes we are interested maybe in the maximum water level or the mean or the quantile, for example, the 50, that would be the median. And Mike IO offers just a function that we have our data array, and we just say NaN max. So we ignore all the values that are empty, that is NaN, and we get the maximum value. Or we can do the same and say ds.NaN mean. So then we get the mean of our time series. Or we can go for the minimum. And here you see as well the quantile. So here we will get the median. And I see here I'm very close now. I've just arrived at the very last plot. I hope you do so as well, because then I can show you what's the output. So we run. Yeah.
Excuse me, Andrea. Just 2 minutes. Such that the run completed. كملت run بتاعت اشتغلت 2 minutes. ده اصلا المفروض نختارها هنا صح؟ ده على الديسكتوب. المفروض من على الديسكتوب سكوب الداتا اللي في ايوه كل دول سيلكت اول. طب بس كمان مصر كان دي وترن الاجلاف تخش بقى على الداتا او الساعتين. المنيو فيها رن تايم. بعد ما عملت جوجل الداتا روح على انلايز اند موديفاي داتا. الصف اللي تحت خالص انلايز اند موديفاي داتا. يوسف بيه وبعد كده المفروض اول حاجه تكتب الداتا كلها. لا الداتا تمام ممتاز. اوكي روح بقى على انا شايف انا بس اللي انت قلت كده روح على ران تايم فوق من ده ومن فوق ران تايم. لا مش ران تايم وران بيفور. ران بيفور ايوه صح دي. معاك يا شباب ده تمام. المفروض انه بيراعي دلوقتي كل الحاجات اللي بتصور. ايوه بالظبط. باشمهندس عبد الرازق ماشي الحال؟ ما كانش معانا بس المره اللي فاتت. كده بصوا على انتوا ممكن تشتغلوا مع بعض الطب يعني عايزين مع باشمهندس عبد الرازق بحيث ان هو عادي فول اب الاكتيفيتيز اللي بتحصل. الليل والدخل. كان في كده ليل صح. فاكرين الفرق كان
Are we on a good way or is there a problem?
الفولدر مغير خلاص. الفولدر كان سيء. انا كله عندي صح. Just wait few minutes to fix all issues. ماشي الحل الكلام ده. انا مشيت راوند 4 على راوند كله كويس تمام كله كده. المشكله في البيت بس. طب ممكن تشتغل مع عشان خلاص القانون مش موجود. انت المره اللي هتخش على الاكونت مفيش اي حاجه مرتبطه بالكمبيوتر اللي هو ده بيعمل تبديل دلوقتي. لا انا ما بيشتغل هتلاقي كل حاجه على البنك وكل حاجه على الديسكتوب هنا. يعني انت عضو جنب بعض خد النص بتاعت الكلاس بحيث ان انتوا هتبقوا قريبين من بعض. هتلاقي اللينك هنا على اللينك اهو كده. هتدخل منه خش على اي كده. كده ماشي حاجه مش مساحه يبقى سيادة طبعا عدد شوف يعني انا مش عارف الفانكشنز او كده بس Is it possible to make zoom in for your screen in large font size or something like this?
Like this?
Please again, more.
More? I guess now you don't. Maybe I switch.
Yes. Yeah.
No. Now I've lost it. So here, like this. Do you see it now?
Yes, this is كويس كده معقول ولا؟ If you more a little bit more.
Try. I gave my best. But then I don't see a lot, not anymore.
Yes, this is very good.
Is that good? Perfect. So, are we here, everybody?
Okay, now we can continue, please.
Okay. So, as I said, like we get like basic statistics from the time series. I added here a short description, but I guess it's more interesting if we just see it. So please run this cell here. And here we print the maximum. And we get the maximum of each. It seems like that the maximum is calculated because it has no time anymore. But we don't get the data here in the maximum. We have to create a table. When we say maximum to data frame, then we get a table with the maximum of each of our variables. So we get the maximum of the wave height and the water level and the wave periods. That's nice, but what's even better is we can use the describe function, ds.describe, and then we get the statistics over all interesting parameters. So with one line, we get from our time series the number of points, the mean value, the standard deviation, the minimum value, and the 25 and 75%.
Please, slowly, step by step, slowly. Don't go fast.
Okay.
Such that we can keep track with you.
Yeah.
وانا كنا في الاناليسيس وبعد كده ها create a table قبل mathematical operations.
Since I see you on the screen, may the people where it worked may raise your hand so I see that it works for some of you. Okay. Shall I continue?
Yes, please.
Okay. So for me, I guess that's quite a good feature because whenever you analyze any kind of data, if you get all the statistics with just one line, that's quite powerful. But we can do also or carry out mathematical operations with this time series data. We can add a value. For example, we can shift the time series by, I don't know, a certain value. We can subtract the value. We can multiply. Or we could also add or sum up one time series with another one, whenever that's necessary. Ruben, you are not muted. May you mute your... yeah. Yeah. So let's see what we can do with this kind of mathematical operation. So we go to the first example. And then here we calculate the surface elevation in millimeters. Okay. Are you still with me?
Yes, ma'am. With you. Yes.
So,
Okay, please go ahead.
okay. So when we don't remember, but the surface elevation is in meter, and sometimes it's important that we convert it from one unit to another. For example, here in this example, I want to show you how to convert it to millimeters. So first, we get just all the data from the water level by this syntax. So we call the DS, that's our time series, and then we mention like the item we're interested in. And then we see what's the maximum of this item. So we just use the max and the values. And then we also see what is the unit. So we run this cell. And let's have a look. Before we convert it to millimeters, we have a maximum of 1 meter 47. And the unit of our time series is meter. Then we create a new time series called ds_surface_millimeters by just multiplying the entire time series by 1,000.
Slowly, because we listen to you, then we apply. So
Okay.
you are applying only, but we listen
Okay.
and then apply.
Yeah, I would suggest that I go through it. It's like 3 times, and then you go through it by your own, and then I continue, and then I take a short break, and then you can push the button yourself. Is that okay? Okay. So here we do the multiplication by 1,000, and next step, it's also written here, we have to change the unit, because if we just I can also add this. When I run it again, then we see what's coming out. Here we still see that we have the water level. And we have to modify the units of our data frame or of our data array. So here we say from our surface data array in millimeters, the item.unit, and we specify it here as millimeters. We can run that. And then we run just a check. So I print the very last time. After the conversion, we have a maximum of 1,475. That's 1,000 times higher than before. And we have a unit of millimeters. Okay, so let's do it now together. Please, everybody, run the select water level, this cell.
اوكي انتوا متفاهم معانا ايه اللي بيحصل؟ هو احنا عايزين نستخدم البايثون في عمليات الماثماتكس، ضرب وجمع وطرح وقسمه. فاكزامبل ده ازاي نحول الووتر ليفل من متر تو مليمتر. ان احنا نضرب طبعا في ألف. فهي عملت ايه؟ اختارت الووتر ليفل في خطوه select water level اللي هي تحت example 1. example 1 calculate the surface division in millimeter. عمل DS surface اللي هي select the water level، وبعد كده طبعت الانفورميشنز اللي هي الديفولت. احنا في خطوه select the water level ماشي بعد السيشن. عندكم نجمين في ايش عندك دايره؟ اوكي Ibrahim? Okay. Go ahead.
So everybody achieved to get the surface elevation in millimeters. Perfect. Then next point that can be important is that we are also able to interpolate in time. Maybe as Ruben mentioned, you have the sources from you have different sources, different time steps, and then you want to have all in the same. You want to have all the same time step. So we can first check what's the time step of our time series. So we just use ds.timestep. So please push that button, and then we see that the current time step is 3,600. That's in seconds. So in other words, that's 1 hour. Every hour we have a data information. But maybe we need to have it not every hour, it is more convenient to have it every second hour. And then, if we want to have this, we can use DS, like our time series, dot interp time. And here we define the number of seconds that we want to use as a time step. So here, when we run this cell, we see here that the new time step, ds.timestep, equals to 7,200. That's 2 hours. And just because it's so funny, we can do it also the other way around. We can also like interpolate, like to give a smaller time steps, even though we don't have any data. So we need to know we don't get new data. It's just an interpolation. So it's so we can also select smaller time steps than we had originally. So here I select 600 seconds, and then we get time step of every 10 minutes. Okay.
time step عملناها دلوقتي البارامترز بتاعتك بتاع الدي اس اللي هي الاوتبوت فايل كله بتدخل داتا في النص الانتربريشن هتدخل داتا في النص او تشيل داتا يعني بدل ما تبقى كل ساعه تبقى كل ساعتين بدل ما تبقى كل ساعه تبقى كل 10 دقائق فهي بتنتربريت يبقى هي كده الملف بتاعك انت شغلته يعني نعمل برنت للملف اللي هو اكسبورت دلوقتي ايه بقى دلوقتي انها تعمل له اكسبورت او برنت. Can you show us printing for a sample from the data after interpolation process?
How it looks like? Yes. You can add a code cell. We say ds min.plot. Now it's quite a long time series. Seems like it needs some time. I need to check whether it's. And now we don't see a lot. It still looks the same in the plot, but we can go. Maybe we see it a little bit better when we just select the water level. So I select here the water level, and then I convert it to a table, I guess, so we see it the best. So here we have the interpolated time series. I select the water level, and I create a table out of it. And here we see we have a time step of every 10 seconds. If it's too small, I guess I can also use it like this. Then you see it. If you don't select the water level, So you don't have to write so much. If we do that like this, then we get the time series of all the different variables we have within our DFS0 file. And here we see we have every 10 minutes time step. This can also be used if you have non-equidistant time steps and you want to make them like equidistant. So just use this interpolate time. Yeah. Did this example work? Okay,
انا عرفت تبع التايم ستيب كل 10 دقائق جيت شغال ها لو عايز بعض بتاخد التكنيكس اللي هي دي بقى لان هنقول لها الدكتور اسمه كده في مشكلة هنا Okay, go ahead.
perfect. So for all of you who want to practice a little bit, there is an exercise which like how to where we have to convert the direction from degrees to radian. And then, but I guess what's also important is now you remember we have converted the water level to millimeters, and maybe you want to use that data series or time series in your next simulation. So we need to get that out of our Python and have it on our disk. So with this command to DFS, the output is saved. So here we just see here the cross. But if we go here to files, and here it should be, I guess it's this one. You don't see it so much, but you should also now have surface underline elevation dot DFS0 here on the right in your folder if you run this cell. If you run the next one, files.download, you get the files are downloaded to your download folder. So you run that one as well. It takes some time. And now I see here at the very top of my Google Chrome that we have a new download. So I go into folder, and now I see here the surface elevation. And you can open that one as every other DFS0 file, and you can use that for further calculations. So I open it, and here we see we have a time series from 2010 to 2019, and we see we have the water level, that's the name, and the unit is millimeter. I mean, I strongly recommend to always update the units if you change anything in the units, or so that the next person who uses the data knows what kind of unit the data is. Okay. Next, sometimes you don't want to have a DFS0 file because it's not always readable. It might be more convenient to have Excel or a CSV file, especially if you want to share your data with people who are not so much into Mic or Python. So to do so, we have to convert our time series to a table. We've done that already, but we do it again, and we store it in the variable called df. So with this command here, we get this table, which almost looks like Excel, and we can just say df.to_Excel and give it a name, and then we get an Excel file. Sometimes the time series are very long, and Excel has problems with open very long time series, so it can be more convenient to export CSV data. So the command is more or less the same. It's df.to_CSV. We run that. And now we should see here on the left that the data is generated. It takes some time because it's quite a huge amount of data that we're exporting now. Give it. And now let's see, where is it? I don't see it. Here, dfs.csv. And if we want to download that on the computer, we can use the same command as above, or also here, there's on the right of each data file, there are the 3 dots in a vertical line. We push that button and we can say download, and then the data is downloaded. You see also here, in my case, it needs some time, and then we can open. There's my mouse. We can open that one the same as before. Did that work for everybody? Yeah.
يعني ها هنا بيقول ايه؟ لا هو الاول لازم نسميها ده كان الفولدر انا كده بيقول الفولدر ده مش موجود عنده لسه السيري دي الخطوه دي لسه ما عملناش تاني واحد احنا لسه ما عملناش لسه ما عملناش اصلا الخطوه دي لسه ما عملناش اصلا معاك.
Okay, I guess I can continue. Here on my screen, you see just the CSV that I exported and downloaded. So this is probably quite useful if you want to do, or if you want to share the data with somebody who's not using Python. And then it's a normal Excel or CSV file, and it's easy to plot and everything. So we are able to get the data and information out of it. The other way around, as Dr. Sami just showed, like how to create a DFS0 file with Mic0, we are also able to do that with Python, and that's especially convenient if we have to do it for several files. So we don't have to do it manually. We can do it like in one step. First, we read the CSV data we have here, and let me see whether I have it here. That's the Ocean Ops data, and as some maybe remember from last time, we have to delete the data with the 2 backslashes before, otherwise we can't find the data. So we read the DSV file. That's just like we load the data into the memory, and then let's see what's the data look like. So, do you want to repeat?
الفايل نيم لازم تاخده كوبي من على الشمال. يعني انت روح على الشمال معايا يمين خدت الفايل نيم من على الشمال كوبي فايل نيم. ها؟ كوبي باك وتحطيه هنا. اوكي؟ عشان بيختلف من جهاز لجهاز. هتضغط على الفايل وتاخدي رايت كليك كوبي باك اللي هو الاوشن. لا الاوشن او بي اس. الفايل اوشن او بي اس على الشمال. اعمل له كوبي رايت كليك وكوبي باك. لا مش خلاص. اوكي كده جميل. كنترول في معايا يا جماعه. بس انا مش بستخدم مكتب. بس هو في الناس في المكتب في بايثون سي شارب. كل دول بدائل. لازم تستخدمي بايثون او مكتب وسي شارب. فعلى حسب انت انا بستخدم سي شارب وبستخدم مكتب. بس كان برضه معاهم ريشنز معاك شويه. ما مش عارف يعني قصدي ما جربتش لسه. انا مش فاكر. طب يعني انا مش اشتغلت بايثون. ما هو يعني قصدي يبقى معاك انا مش يعني بايثون مثلا لو تعويض بعد كده بتعمل بس تعمل اكسبيرينس. ممكن البايثون فيها ميثود سرعه يعني. يا رايت. كده بدل ما تستخدم اكسبيرينس طبعا يعني انا حسيت ان انت تاخد هتحتاج تشتغل فيها حتت صغيره. المشكله ان انت فكرتني ساعتها انت مش هتفتح هو كتب بس يبقى طويل. يعني البايثون بيبقى على اساس ان انت هتعمل بارتيشن تاخد بارت يعني تاخد جزء تفتح الجزء الصغير اللي انت عايزه بس.
Okay, so we all push that button, we run the cell.
Yes.
And now we see what we get. We get a table. One column is called time, and the other column is called water level in centimeters. And then we have for each line we have the row index, and we have the data and the time and the water level. If we use the plot function, as I did here in the last line, we see how the data is interpreted. I need to zoom out a little bit so that you see it. And what is very important here, it is not recognized that our time series is a time series, because here we don't see the dates, we just see the numbers of the row index. Here that's just a string for Python. It does not know that this is time, so we need to tell it. So let's check how it looks like. So we say df.time, so we just see the column with the time data, and here we see the D type is object. And now I zoom in again so that you can see it a bit better. We see that the name of our column is time. We have a lot of lines, as you see here in the length, and the time is an object. But we want to have it as a date time, so that we see that it is interpreted as a time. In order to do so, we need the command to date time. And we say that our column, all the data in our column that's called time, has the format year, month, day, hours, and minutes. Because we see here, we have here year, month, days, hours, minutes, and also second, but we just leave that out. And then we run this cell. And in order to make it easier to plot, we say that the index here, we don't need here the numbers. We say our time series consists only time and the value. So this is done by this cell, and we plot it. And then what we get is here on the x-axis we get the time. We get the different years, and that's a super check to see that the data we imported is read and interpreted correctly.
هو احنا الهدف من اللي حصل اول حاجه احنا فتحنا التكست فايل ولما فتحنا التكست فايل حبينا نتفرج عليه زي اكنه في اكسل بالظبط. فعشان نتفرج عليه رسمناه. فلما اترسم المحور بتاع اكس كان مش التايم ستيب، كان الرو نمبر. يعني كان ايه 1 2 3 شايفين 0 1 2 3 4 ده كان الرو نمبر، لان هو مش فاهم ان ده تايم، فاحنا عايزين نفهمه ان ده تايم. فعملنا ايه؟ رحنا محولينه تو set index df دوت تايم، يعني حوله للتايم. وبعد ما حولناه للتايم رحنا قلنا له بلوت مع التايم بقى. فالتايم فيجر كان بقى مختلف، كان بقى بالسنين تحت 2004 2000 بقى محور اكس بالتايم مش بالسيريز بتاع اوكي. لا هو انت لما رفعت الملف، لا الملف ما انت لازم تاخد كوبي، خد كوبي باست فايل. بص انت خدت ده يعني، لا هو ده كان ماشي من الملف على الاسلوب ما بس سوي شويه انت برضه ما تنساش نفس معايا. لا انا هقول لك الملف اللي عندنا كان اسمه اوشن او بي اس. اوشن اي بي اس. ايوه ده كنترول هنا كاتب بعض. ايوه كنترول بي بعد مثلا ماشي معايا اهو. وبعد كده هنا بقى الران دي بقى على طول ايوه تحت الرن دي الرن ده دي كمان دي طبعا ديزاين تيم دي خلاص كده عملتها لير ومانث داي وبس. وبعد كده ايوه دي بقى المفروض بقى محور اكس دلوقتي هيظهر لك بص اللي بقى تحت. بص شايف محور اكس بقى فاين. الاول كان ارقام اللي هو السطر رقم السطر. هم ده بداية يا اما تشتغل يا اما بداية يا اما سي شارب بس ليه احنا لما نقدر يعني لو درسنا المثال بس لازم هم يعني لازم تبقى معاك لايسنس المثال ما نفس لايسنس المثال صراحه تبدلها بالسي بايثون عشان ما تمشي لايسنس فممكن انما يعني ممكن مثلا Okay.
Okay.
You can go ahead.
Okay, maybe we want to use that data in our next simulation, and then of course not in centimeters, the water level, but in meters. So therefore we convert the water level by dividing it here by 100. So we create a new column of water level meter, and then we plot it as well. Takes once again some time, and then we see here on the axis it's the values are 100 times smaller than here, so that worked. And now to use that as a DFS0 file, we need the following syntax. We can say our table, that is here the DF, to DFS0. We can define a file name, and we define the items. That's like the information in the columns, and we say our item info. That's the name. The first one is the name. We want to call that the water level in meters. We say the type is water level, and the unit is meter. So everything that you can also do in Mic 0 with the different boxes, and then you select. You can also do here just by written language. And then you run it. And let's see, it should somewhere appear here on my list. Maybe it does. Water level.dfs0 to DFS. It needs some time, and so it popped up here on the left. And we can download that directly by the next cell. It's downloaded to our downloads folder. And we are able to open that on our own computer, and we keep that data that we have downloaded. Everything that is here on the left will disappear as soon as we close that session. Therefore, it's quite useful to download the data. Here we see it's downloaded. And I open that one quickly to show. Yeah. So here we see, and here's the name as we wanted to have it. And we also see meters is directly added from the information that is the type unit meters. I hope that worked. So we can jump into the 2D time series. And we need a timeout. Yeah?
Please wait.
Yeah.
ايوه بتبدلوا مع بعض اللايسنس يعني اللايسنس تبدل من جهه لجهه عشان هو اللايسنس عددها اصلا احنا معانا 4 يوزرز واحنا ما شاء الله عددنا اكبر من كده فبالتالي وانت فاتحه الجهاز بتاعنا ده احنا اللايسنس الاول اللايسنس ده
احنا خدناه سطرناه مش تقديم
بس انت عملت اللايسنس بتاعك
ده كده خلي
اوكي كله دلوقتي فتح الملف على الديسكتوب عمل داونلود اوكي اند جو اهيد بيت
Okay, so now first I want to show you the difference between a DFS0 file and a DFSU file, I guess you know. So therefore we load the two files, and the DFSU file is the one called North Sea, and the DFS0 file is the waves and water levels. And in order to import it, we need to once again delete this data in front of the line. And you should have already drag and dropped the North Sea data so we can run. And when we look at the print, here we see that the DFS0 file has a time axis and has items, but has no information about the geometry. So it's just like an Excel, time, and different data. On the other side, the DFSU file comes along with some information about the projection, the number of elements and nodes. So the mesh that is used to generate this DFSU file is also saved. And we have the items. We have here two. We have the surface elevation and the wind speed. And we have 67 time steps. So which is not a long time, but I guess it's just handy to have a very small file to have it imported quite easily. And so the main difference is that the DFSU file has a geometry. I can just quickly show you how it will look like. That's if we open the file in our browser. And here we have the surface elevation. I know it's very small. And the wind speed, that is exactly what we've also seen here, the items, wind speed, and surface elevation. And now we can use the geometry information to investigate the geometry, of course, and that's really useful. So at the very first, we retrieve the geometry information by calling dfsu.geometry. Then we have a geometry file. And I print the information that is stored in it, and I plot it. And we get this.
Okay, just 1 minute. هو دلوقتي المرحلة دي احنا بنشوف ايه دي اف اس يو فايل. احنا عندنا اتعاملنا مع دي اف اس 0 دي اف اس 1 ودلوقتي هنتعامل مع دي اف اس يو. فالدي اف اس يو بيبقى فيه جيومتري، يعني ممكن يبقى فيه ماشي. يعني بيبقى مش ومعاها داتا، فمش داتا. اوكي؟ فهي بقى هنا بتوريك فتحت الملف ده. طبعا عشان تعمل رن الملف من البدايه لازم تاخد الباب. اي ملف، يعني هنا بص الباب ده الملف ده اسمه تي اس ويفز. فين التي اس ويفز ده؟ ايوه سبورت بار بالظبط كده. ايوه كنترول بي وبعد كده رن. لحظه ماشي. طلع الدنيا يعني واخد بالك؟ لان كل واحد فينا الباب بتاع الفايلز بتاعه بيختلف من واحد لواحد. اوكي؟ فهي فتحت دي اف اس يو فايل وطبعت جيومتري وقارنته بالدي اف اس 0 اظن. ودي اف اس 0 لا بتاع اللي فوق 0 شايف ده؟ ها؟ طب لحظه اسم الملف هو
لا مش عارفه.
ده نورس والتاني تي اف. بص تاني اهو. فين النورس؟ النورس ده هو ده؟ عايز تاخد بقى. ايوه ده يعني هو دي اف سي. ايوه كنترول دي. بص لا تاني امسك ده كله. خد كده دي بقى دي. ماشي كده. بناخد الفرق بتاع كل ملف لوحده. الزيرو في الاول واليو تحت. اوكي. لا احنا هنا بنقارن ما بين ملفين، الدي اف اس يو كستراكشر شكله ايه، والدي اف اس 0 كستراكشر شكله ايه. فلما بتبص كده بتلاقي فوق في اول مجموعه سطور بيكلمك على الدي اف اس 0 ده فيه عباره عن 4 معلومات لكن ما فيهوش جيومتري خالص. انما لما تنزل بالملف اللي تحت يقول لك فيه ايه؟ نمبر اوف اليمنتس، نمبر اوف نودز، لونج لاج، والانفورميشن اللي عند كل نود من دول عباره عن ايه؟ اللي هي السيرفيس الفيجن والويند سبيد. وعندي تايم ستيب عندي 67 67 تايم ستيبس. بدات واضحه المعلومات سؤال؟ ويا ريتني نران لغايه الفيجر ده. يعني نران لغايه ما الفيجر ده يطلع منه. ايوه.
يعني هو بيجي برنامج البسمتي عشان يكتب قدامك تكتب كده. بس اي حاجه
لا دلوقتي معانا لغايه دلوقتي كده ان ممكن ده بسمتي صح؟ ده بسمتي. فين الويند سبيد؟ الويند سبيد. Excuse me, can you illustrate the wind speed in this in the shown statement DFSU 2D? You plot the bathymetry. Okay.
Yeah, that's very important because when you open the DFSU file with the mic 0, you don't see any information about the bathymetry, right? It's just the wind speed and the surface elevation. But when we open that file in Python, then we get an additional information. We get all the information about the mesh that the data is based on. So we can discover the bathymetry that was used to generate this DFSU file. So like and that's some additional information we get that actually, at least I don't know how to get it from the DFSU file from mic 0. So we get information about the geometry, like long latitude, projection, but we also get some information about the sea bed in this DFSU file, which can be really useful. And so we can, for example, I have added some example how we can use that. Sometimes you might be interested to find the deepest point in your mesh that you used. So
can you write the same plot? Can you redo the same plot for other for wind as example?
Yeah, we're gonna do that later.
Okay.
That's here. Actually, I mean, it's up to you. We don't have so much time left. We can also skip all the part about the geometry, like how to find the deepest point, to export the boundaries, and check whether a point is in the middle.
We have extra 1 hour.
Okay, that's okay. So we just go through the geometry, and then we're going to continue and see how to really go to the data. But I wanted to show you the thing about the geometry and the bathymetry, because this is something that makes it very special. So then let's continue, and we find the deepest point in our area that we have in the DFSU file. In order to do so, we can extract the coordinates of each element center. To do so, we create a table, and the columns are called longitude, latitude, and Z. And the data is data, geometry, and node coordinates. So we get the coordinates of the nodes. So we run that, and we get a table of all the nodes in our mesh, with the longitude and the latitude information and the Z. So that would be the depth. And apparently I also plot it, as you see here. And it doesn't really make sense. We have like the orange, we have latitude around 50 and longitude around 0, and we have the set elevation ranging from 0 to -90. So we expect to have the deepest point around -90 meters. So to get the deepest points, we just say coordinates. That was our table. We point to the column called set, and we call it min. So we get the minimum. And we see I was not so wrong. Our deepest point is -93 meters. But next question is maybe where is that point? So we can say from our coordinates, we select the coordinates where the set, from the set column, which is exactly our deepest point. And then we get the longitude and the latitude and the set level. And furthermore, we can plot all together. We can plot the geometry we've already seen before, that nice colored plot. And we can add the point that we just discovered so that we see where is the deepest point. And here we see, actually, I guess we've already guessed before, in the northwestern part here at the very top, here is the deepest point, and we see it here marked as a red point.
Excuse me one minute.
Yes?
And I get maximum depth. What is the location of the deepest point? انا عايز اللون ده بقى تحت. يعني السؤالي الفاليو والثانيه the long lag of its value. اوكي؟ اللي هو اللوكيشن. خلي بالكم من وبعد كده البلوت ازاي بقى عملت كومباينيشن ما بين البلوت
جمع صغير يعني حط النقطه دي اصلا على الكويس
بس هي الخريطه تقصد بالخريطه
كان فين
ده البلوت بتاعها بس انا قصدي الامر بتاعها كان ايه؟ بلوت جيومتري بالبلوت اكس سكاتر اكس دوت سكاتر اكس excuse me, can you elaborate a little bit the plot command, this plot command?
Yes?
You combined here in this plot command the bathymetry with the point.
Yeah.
Can you elaborate these commands a little bit?
Explain. Okay, first we create the plot like the geometry we did before, but then I store that in the variable ax, so that's like the figure. And we need that because now we can add another plot to this figure. So therefore we need this ax, and then we say ax, and here we say we defined a specific plot that's called scatter, that's points. And here we define the x coordinate or the longitude, and here the latitude. And then the third is the marker size, so it's 10 points. And here see we define the color. And with the label, that's the description that will appear in the legend, and we just choose the value. And this works because we have only one item here. We have just one line, so it will plot 1 point because it's just one. With the longitude, latitude, and the set is used as the description in the legend. And here we add the legend as well to the plot. If we don't use that command, we don't have a legend. So in order to see the legend, we do like this. And the description of our plot in the legend is used as a label.
Yes. Great. Okay. Now go ahead.
Yeah.
Okay, go ahead.
Next, in my opinion, useful feature is that we can also export the boundary of our mesh or of our DFSU file as a shapefile or a geopackage file. So first, with this command, like the geometry, that's all the data that is saved in this geometry information. We use geometry.shapely, and this creates shapes. Like each element consists of a polygon. That's the first step we used to do. Then we merge them by using a buffer. And here you already see the plots are not so nice, but here we have one polygon covering the entire model area. And then we can create a geodata frame. That is just one step we need to do for the export. So we create a geodata frame. We have the feature that is 0, there will be 1, and the geometry that will be used in is the domain. That's this polygon here, and I will plot that. And we can also define the coordinates. So here I use the coordinates 4, 3, 2, 1, and I set the coordinate system. And here we see the output, and we can write that to a geopackage file. I know these steps are very, very fast now, but it's just I just wanted to show what's possible, and we can now discover that in QGIS. I just show you. I have prepared already the map before, and I can now, hopefully, I haven't tested it, just drag and drop here, and now we see where we are with our data. So we are between the United Kingdom, Denmark, and Northern Europe, or Netherlands and everything. This part is covered by our model. And this is the extent as a shapefile.
QGIS. Yes?
Yeah. So, yeah. I just wanted to show that we are also able to extract information from this DFSU file that we can directly read in the QGIS.
Is it possible to make it as a shapefile format?
Yeah. Actually, you just if you want to have a shapefile, you just need to have here .shape. That's exactly the same. I just used geopackage because then it's just one file to download. Otherwise, then we have always 4. Because a shapefile consists from .shape, .shx, .dbf, and here it's a bit more convenient. But yes, we can also say df to file. And here you will see that we have a shapefile as well. And then we get the projection file, the shapefile, and the SHX and the DBF. And everything is a bit more compact if we use the geopackage format. That's just why I use that. A third useful application can be that we can check whether a point is within our model boundary. For example, if you have measured data and you want to know whether this measurement station lies within your model boundary and you can use the measurement or not. Therefore, we have a check if the point is in the model boundary. To do so, I create 2 points. With this command here, we have points equals, and then it's longitude, latitude, and we have 2 lists, so 2 points. And the only thing or the only command we need, we can say geometry dot contains points, and that will give us the answer. So I just like this. So first, if we run the first part, then we will see the first one is true. So the first point will lie within our model boundary and the second point doesn't. We can trust that or not. So we add this the check here, the plot. So we do the same here. I define two different colors, blue and red. And then I first plot the geometry, like the bathymetric data. And then I loop through the points, point 1, point 2, and I create a scatter point, one scatter point, and I use first and the second, and the color is the first and the second. And the label I use is whether it's inside or outside. So let's check what we get here from that plot. We have a blue point that is has the label true. That was the first one that lies within our model boundary, and the red one is outside and it's called false. That's just another application. So then I had added another exercise you can do, but now we come to the point where we really read the data you were asking for, like the wind speed and the water level. Up to now, we had just discovered the geometry. So in order to really read and load the data, we use mike.io.read. And we have once again to delete this data part in front of that, as we've done before. Please run that cell and the next one as well. So you see on your screen what we have. We saw that already before. But we have now a huge file, and sometimes we don't need to have all the different, like the 2D information. Sometimes we are just interested at points, maybe if we have, as I've already mentioned, a measuring station, and then we just want to extract the information at given points. So we can do that by creating a points list. And here I say points, I go for the first item, that's this one, and I select the first item in the list, that's 0. So this will give me my X coordinate and my Y coordinate of the points. And I read the data, delete this part. So mike.io, I read the file, but I just go for the information that is stored in the X coordinate equals to this information and the other one. So here we get a 1D data because it's just the information of one point, and we get the wind speed at this point and the surface elevation.
فيها مشكله لازم الباث بتاع الفايل لازم يتغير. فايل باث او كوبي فين؟ اللي هو اسمه نورث يعني ياخد عن نورث وكوبي مكانين تو لوكيشنز.
المفروض يدفع في ساعات مثلا لو في امتحان من هنا كمان مش وانا مش متعود بس بيبقى هم الكويس اللي احنا علينا فانت لما كانوا بيشيلوا يزيدوا مثلا لا عايز تطلع لا ده مش طب بقى كنت كده تطلع بس صوتك كويس مش لو مش زود الكومنتس أصل ممكن يكون ده إكس دي حاجة اسمها الفاريبل راندوم فاريبل إذا عرفت الإكس ده مش الفاريبل فاهم إزاي؟ أوكي معانا كله تمام؟ مين طيب okay please go ahead.
Okay, so we've chosen the first point. We remember there was the one that is within our mesh. So just out of curiosity, change that one to the second point and then run again. And here it gives you an error. It tells you that the point is not within the mesh. So that's good, because I was expecting that it just gives any point, but it really checks whether the point is within our model domain, and if it's not, it will give us an error. So I change it back. Voila. And we have that one. So now we come to the probably most interesting part. Oops, I do it like this. The following thing that worked for the DFS0 file, that we just say ds.plot is not working. I will show you here. If I run this command, ds.plot, gives us an error. Why? When we just go quickly back to what kind of data we have a geometry. So we have a 2D data, we have 2 items, and we have different times. And we have just too much information to put in one plot. Therefore, it gives us an error. And we need to specify a bit more what we want to plot. So this gives an error. I comment that out so that we have it here. But if we, for example, say we select the first item, so we seen already we have the item wind speed and water level, I guess. Surface elevation is the first one, and the second one is wind speed. And we can select the first item by saying ds.items 0. So we get the first item here. First item is our surface elevation. And when we want to plot the first item, we say ds, and then we define the item we want to plot, and we plot. So here we plot the first item, the surface elevation. And when you run that, you see here at the very top the time step that is plotted. So here it's the time step 2017, the 27th of October. And by default, if you don't specify the time, Mike.io will always just plot the very first time step of your data. So you just get like the beginning of your simulation. Can be useful, but maybe we are sometimes also interested in maybe the, I don't know which time step, or maybe we are also interested in seeing like how does it look like when we have the maximum water level. So here we say ds items dot max, so we get the maximum over the time at each point, and we plot. And we just have to ignore here the header because that's wrong, but we see that that's the maximum surface elevation. So we have here in the eastern part, we have 3.75 meters, and here it's a bit lower. So we can also directly plot the maximum, the minimum, the mean, I don't know what. That's quite useful. That's about plotting. You can choose the item, you can choose the time you're interested in to plot. And sometimes you may realize I'm a bit a QGIS fan. Sometimes it's also useful to have this data in QGIS, maybe because these plotting functions are nice, but they are also a bit time consuming to make them really pretty, because maybe we want to add a north arrow and everything that gets really complicated. So I would recommend to export the data, for example, as a TIFF file. And to do so, a TIFF file is a file that has a regular grid. Therefore, we first need to convert our mesh, irregular mesh with different points around, with different distances, to a regular grid. And we do so while we define our grid resolution. I call it TIFF resolution. We define the coordinate system that our TIFF should have. Then first we create an overset grid. So we overlay a regular grid over on our data, and then we interpolate that, and to check what we've done, we plot that. So I hope it doesn't take too much time to do so. So here we see we have now not the same picture as before. It's much smoother. And so we can now play around if we select quite a coarse resolution, for example, 0.1. And since we have a coordinate system of long lat, that will be 0.1 degree. You see what we get? Then it's much coarser. Or we can also go for 0.1, then it's really fast, I guess. Then it looks like this. Not really useful anymore, of course, but here you can also define like what resolution you're really interested in. I go to 0.1, and we see here the grid. Of our water levels. And then next time we can export that as a TIFF. We need the raster IO function. We need to define the name of our TIFF, the driver, then the number of Y, like number of cells on the height, and the width is then the number of cells along the x-axis. Then we define different here. We can define the coordinate system. That's quite useful. And we need to define the transform. That's, I don't go into detail. And then with this function, we can export our data. So here, I used my data grid and I took the maximum value. That's the data I want to export. So I want to export the maximum surface elevation. And then I call this function and I hand over the data to export, and then I run it. And I guess if we look now, that was really fast. It should here appear max surface elevation as a TIFF, or we can download it again with this command here. Pops up here. And I can show you that it really works. Because I'm just drag and drop it to my QGIS, and then I just select some. And now we see the maximum water level within our very short time span of our simulation. And we see that here between Hamburg and Bremen, it was the highest in that period. So we are really able to, with not, I mean, you need to know the syntax here, but as soon as you have it once, you can reuse that many times and for all the different projects you have. And you get a TIFF that can be easily used in QGIS and can also share to others in the team who are not really used to mic. And you don't need a license. I mean, you don't need a license of mic to use everything here in Python. That's also quite handy because we are able to read the data and convert it to something, to other formats that can be used without any license. And also, like if you use QGIS, then you can use that also for free. We do that so, and it's really, yeah, useful. Okay, that worked. Cool. I guess I'm gonna skip the next part because we've already somehow covered it. It's a bit a more applied example, extract time series at specific points if you have the points as a shapefile information. But I will I will jump that over, and I want quickly just cover another application that would be the extreme value analysis that can be very easily carried out with Python because there are so many libraries that are already implemented and can be used, and they are as well for free. And I've chosen to show you the library PyExtremes. And this library allows us to extract like extreme values in a time series and to fit a probability distribution on this time series or on the extremes and get the return periods. especially if you are not so much into statistics. It's an easy way to get a certain kind of information. Of course, in order to interpret the data, you need a bit more profound background, but to get like a first idea what a return period of 100 years could be, is that quite useful. I've also mentioned here an alternative library where you have a bit more freedom, is scipy.stats. You can use that one as well. Yeah. So we start by first reading the time series we want to analyze, and that's once again the waves and water levels we've seen already before. So just load the data, and we need to have the data as a table. So we use to data frame, because here we see it's like this 1D time series. We can just use the data frame, and then we get once again this table we've already seen quite often before, with the time on the first, and then with the values. And now it goes very fast because it's implemented. We create some kind of model. So we say we want to define an extreme value analysis or carry out on the water level I've chosen. I mean, you can go for whatever you want. If you want to go for the wave height or so, I said I want to create an EVA for the water level. And then next time I say I want to extract all the extremes in my time series, so just the values that are extreme, and there are two different methods. This is the block maximum methods, and the size is 365.2425 days. That's exactly 1 year. So what this cell does, it analyzes the time series, and it selects the highest value of each year and stores it in extreme. And then I can do the extreme maybe, or I can plot it. And here we see for each year, that's the extreme value for year 1. Then the red points show us the extremes that are selected. On the other side, we can also choose, if we know that we are interested for all the extremes which are above a certain threshold, we can use exactly the same syntax. We say the method is not block maximum, it's POT. It's peak over threshold. I've chosen randomly a threshold of 1.1. And I said, find the threshold, find one extreme event within 24 hours. That's like the duration window to cluster the data. And if we run this, you see the line that I've chosen, the threshold line, and then all the data, all the points or the events that are above this threshold. And next, we can fit a probability distribution to these extremes, to the red points. And we can define the probability distribution. There's also a documentation what probability distribution are available. And then we get all the information here. I need to zoom out a little bit. Oops. So we get a summary. So we have the extreme values over threshold. We used the exponential Weibull distribution, and we have got the following parameters. What's now really useful probably is that in this PyExtreme library, they propose to find the perfect probability distribution, the perfect fit for you. So if you don't know what kind of distribution will fit the best, you can just ignore that you have the kind of distribution you have, but you can just say model.fit model. That's if you fit a probability distribution to that, and then you see, in my case of the data, and that's just an example. I'm not saying that this is the correct solution. It also depends on the physics, but it's the the distribution is the exponential one, and there's also you can get the return periods of your fitted model by just say get summary, and then you define the return periods you're interested in, and then you get the return periods of your model level given the distribution you fitted. And if you're as well interested in like to see whether it's really a good fit or not, you can also use plot diagnostics, and then you get an overview of how good the fit is and a lot of other information. There was quite a lot, and it's just like a glimpse of what's possible with Python. If we have like the simulation results, we read it, and then we carry out this extreme value analysis. Because I have some time left, I can cover the very last topic, and we can also now investigate like the joint probability, or just like the table of two different data information. So here I want to have like a table showing how often does a certain wave height and a certain water level is.
ماشيين معاه ولا يعني كل حاجه ماشيه كده. هو طبعا الموضوع دسم قوي، انا عارف، يعني احنا بناخد لغه جديده بلايبرز كتير قوي بس هو الموضوع يعتبر المواضيع المهمه. فاللي بيشتغل مش لازم يشتغل بايثون بس بس هو يعني هي متمكنه منه وعارفه يعني ايه تساعد كتير.
مثلا بيقولوا لي جهاز اسمه بايثون 3 مثلا
ايوه، هو بايثون نفسه في لايبرري جاهزه فري اوبن سورس، فدي ميزه. فهي طبعا بيورينا كل حاجه بتستخدم ازاي كده على السريع. ايوه بالظبط، جد الفاليوز عند التيري فاليوز مختلفه، ورسم البوكس بتاعتها. اوكي go ahead.
Okay, so our goal is now to see how often a certain wave height and the water level is exceeded or reached. Therefore, we just select the two information like the wave height and the water level, and we reduce our table to just the two informations, as like two variables. So we have the wave height and we have the water level. And now it's going to be a bit complicated to create the table. We define that we want to have like water levels binned into 0.5 meter, and as well the wave height, that's the bin size. And we create, I run that thing. So we have a minimum wave height of 0.01 meter and a maximum of 2.3, and therefore I choose bins between 0 and 2.5. And we will count the data and put the data like numbers that appear within this range. We do the same for the water level. So we check what is the water level. It's between minus 1.21 and 148. And then we create this kind of bins. And then we create an empty table that we're going to fill. So we have, let me check. So the index is the water level. So this one is the water level here. And this is the wave height is on the X, or like the columns are the waves, and the rows are the water level. And we're gonna check which data point will fit into the different bins. Therefore, I'm gonna loop through all the data, and here I'm gonna check whether my water level is greater than the bin size I'm looking at, or smaller than the other boundary, and I loop through that. I guess you just, and what we get at the very end when we run that code is we get the numbers. So a wave height between 0 and 0.5, and in the same time a water level between -1 and -0.5 meter appears in my data set 10,414 times. And we can then clean our table so that we reduce the values that are not existing, and we can also calculate the relative exceedance, so we just divide by the total length. And we can check whether our table is reasonable, so we just cover almost all the data, almost one. I guess the smallest value here was smaller than my very first bin. Yeah, so I should choose actually a water level -1.5, and in the very end, just to show you, we can plot that as a heat map, so that we see here this, like, different colors show the number of appearance, and here we see, like in the relative case, that we have most of the data, or most of our events, or like most of the time we have this condition here. Yeah, that was now very fast. I guess we would have to deep dive into this term probability much longer to really get into it. This is just an example what is possible, and you see I had to have a lot of code I had to create myself, not like with the extreme value analysis where we had like a pre-arranged setting and we just could use some lines and then we got a good result. So that's also Python. It's not everything is already here, but you will find almost everything on the web that will support you and to find a good way to solve all your problems. Yeah, I guess I reached somehow the end of today. Yeah.
هل في أي استفسارات أي حاجة؟
تعمل احتمالات
التيبلز، يعني التيبل اللي انت شايفاه كنمبر ده تقدر راح رسماه بحيث انت شايف الرقم ده مثلا 0.1.26 and 0.13. لما تنزلي تحت تلاقي الايه البلوك بيبين لك ان المنطقه اللي فيها الويفز بتاعت كبيره هي المنطقه دي.
عشان الحاجات اللي على الشباب.
ايوه اللي هي شال النان علشان ما يبقاش التيبل فيه حاجه يعني اود. اوكي. Excuse me, can you recap the extreme value analysis step by step and slowly?
Yep.
Just repeat the part of extreme value analysis again.
Mm-hmm.
With more illustration or.
Okay, so we start by reading the data that's done here. First cell, we read the data that is in this DFS0 file. Then that can be an output of your simulation, and we convert the data array. I can show you this kind of. Here we have this mic data set, which is not really nicely organized in a table that is easily to read. Therefore, we create this table here by just saying to data frame. and it is automatically recognized that it is a time series because I guess I can say df.plot. I've used that already before, and then we see that we have here the time. So we are really sure we have a time series that is interpreted like a time series. So the tool knows we have a time and we have different variables. And I selected to do the EVA just for the water level, but of course you can select also the significant wave height or whatever you want to. So we first have to import the EVA module from PyXtream. PyXtream, I can show you. It's you can just Google it. And then you find out I don't invent something new that's already there. PyXtream is a library that can be used, and it will there's a huge documentation how you can use it, and you recognize also this plot that I created. So you can import that one from PyXtream, import EVA. And first we have to say that that's like we define a class and say like EVA, we're gonna do all our EVA for this part. Just like from our table, we just select one item. So it's just for the water level. I mean, we can do the same thing also for, if we do it like this. Then we go for the significant wave height. And then we could here, second step, now we extract the maximum wave height of each year when we defined the method as BM, that's the block maximum method. So every maximum within a block, and the block size is